All right, midterm season is in full swing. If you're looking at a huge pile of notes and feeling that pre-exam panic, take a breath. You're in the right place. Think of this as your secret weapon, your guide to cut through the confusion and really nail these core concepts. We're going to tackle this logically, building your knowledge from the ground up so it all makes sense. No more just memorizing facts, we're going for true understanding. Ready? Let's jump in.
So here's our game plan. We'll start with the physical stuff, the hardware, then we'll dive into the logic and software that tells that hardware what to do. After that, we'll see how networks connect everything together. And finally, we'll wrap up with a quick hitter review to make sure it all sticks. Let's get to it. First up, hardware. We're talking about the actual physical parts of a computer, the things you can literally touch. If you want to understand how a computer works, you have to start with the machine itself. Okay, so right at the heart of everything is the Central Processing Unit, or CPU. And calling it the brain isn't just a cute analogy, it's pretty much spot on. Every single thing you do, every click, every key press gets processed and executed right here. It's the engine of the whole operation. Now, if the CPU is the brain, it has two major departments. You've got the Arithmetic Logic Unit, the ALU, which is basically the master mathematician. It handles all the calculations and logical comparisons. And then you have the Control Unit, the CU. Think of it like a traffic cop or an orchestra conductor, directing the flow of information and telling every other part of the computer what to do and when to do it. This right here is the fundamental loop of everything a computer does. It's called the I-pause cycle. It starts with input, that's you typing or clicking your mouse. Then comes processing, where the CPU does its thing. Next, you get the output. You see the result on your screen. And finally, if you want to keep that result, you save it to storage. Input, processing, output, storage. That four-step dance is happening millions of times a second. Okay, pay attention because this one is practically guaranteed to be on the test. The difference between RAM and ROM. Here's the easiest way to remember it. RAM, random access memory, is like your desk. It's the temporary workspace where you put all the stuff you're actively working on. It's super fast, but when you shut down the computer, the desk gets cleared off. It's volatile. ROM, on the other hand, read-only memory, is like the computer's built-in instruction manual. It holds the essential startup instructions, and it never forgets them, even when the power is off. It's non-volatile. So how did we get from computers that filled entire rooms to the powerful devices in our hands? Well, it happened in 4 giant leaps. First-gen machines were massive things run by hot, unreliable vacuum tubes. The second generation got a huge upgrade with the invention of the transistor, making them way smaller and more dependable. The third gen took it even further, packing tons of transistors onto tiny little integrated circuits. And that led to the fourth generation, the microprocessor, which put the entire CPU onto a single chip. That's what made personal computers possible. Okay, so we've got the physical machine down, but a hunk of metal in silicon doesn't do anything by itself, right? It needs instructions. It needs a mind. And that's where we get into logic and software. Believe it or not, at the deepest, most fundamental level, computers speak a language that is incredibly simple. It's all based on something called Boolean algebra. Now, don't let the fancy name scare you. The core idea is that absolutely everything can be broken down into one of 2 states, true or false, on or off, 1 or 0. That's it. That simple binary choice is the bedrock of all digital logic. And this chart shows how that simple logic works in action. These are called logic gates. For an AND gate to output a true or a 1, both input A and input B have to be 1. For an OR gate, you just need either A or B to be 1. And the NOT gate is the easiest of all. It just flips the input. A 1 becomes a 0 becomes a 1. Every complex piece of software you've ever used is just built out of billions of these simple decisions. Which brings us to this key distinction: hardware versus software. The absolute best way to frame this is to think of hardware as the physical body. You can touch it, it takes up space, and eventually it wears out. Software is the mind. It's the collection of thoughts and instructions that tells the body what to do. It's intangible, and you can update or change it in an instant. And software isn't just one thing. It comes in 3 main flavors. At the bottom layer, you have system software, your operating system, like Windows or Mac OS. Its job is to manage all the hardware. On top of that, you have application software. These are the programs you actually use, like your web browser, a word processor, or a game. And then there's a special category called firmware, which is low-level software that's permanently baked into a piece of hardware, like the code that makes your router work. So, how is good software actually built? It's not just a chaotic scramble of coding. Professionals follow a structured process called the Software Development Lifecycle, the SDLC. It starts with analysis, figuring out what people actually need. Then comes design, creating a solid blueprint. Only then do you get to implementation, which is the actual coding. After that, it's all about testing to squash bugs. And finally, deployment and ongoing maintenance. This process is key to creating software that actually works well.
Okay, a single computer is an amazing tool. But the real revolution, the thing that changed the world, is connecting them together. That brings us to our third major topic, networks.
When it comes to networks, the two big categories you absolutely have to know are LANs and WANs. A LAN, or local area network, is exactly what it sounds like. It's local. It covers a small area, like your house, an office, or a school campus. A WAN, or wide area network, covers a huge area, connecting different locations. And the biggest, most famous WAN of all? Yep, it's the internet. The way you physically arrange the connections in a network is called its topology. Think of it like a blueprint. In a star topology, everything connects to a central point. If that hub fails, the whole network goes down. In a bus, everyone shares one main cable. If that cable breaks, same problem. A ring connects everything in a loop. And then you have a mesh network, where every device is connected to every other device. It's super redundant and reliable, but also way more complex and expensive. Now, to make these networks function, you need some specialized gear. Switches are what connect all the devices together inside one LAN. Routers are the devices that connect different networks to each other. They're the traffic cops of the internet. Access points are what create your Wi-Fi signal, letting you connect wirelessly. And firewalls are the security guards, standing at the edge of your network, deciding what traffic gets in and what gets blocked.
All right, here's another huge one for your exam, TCP versus UDP. This all comes down to a simple trade-off, reliability versus speed. TCP is the reliable one. It establishes a connection, checks to make sure every piece of data arrives, and puts it all in the right order. It's perfect for loading a website or sending an email where you need everything to be perfect. UDP is the fast one. It's fire and forget. It just sends the data and hopes for the best. This is great for things like video streaming or online gaming, where speed is more important than perfect accuracy. To keep all this network communication organized, we use conceptual models. The two you'll need to know are OSI and TCP/IP. The OSI model is the 7-layer theoretical framework. It's like the detailed textbook version. The TCP/IP model is the more practical 4-layer model that the actual internet is built on. As you can see, it basically just combines some of the OSI layers. They both describe the same process, but TCP/IP is the one we actually use.
Wow. We have covered a ton of ground. Hardware, software, networks, the whole shebang. So let's bring it all home and do a quick fire review of the absolute must-know concepts for your exam. So if you're cramming and your time is short, what are the things you absolutely have to lock in? Let's boil it all down.
This is it, your 4-point cheat sheet. If you know these 4 called, you are in fantastic shape. 1. The CPU has the ALU for math and the CU for directing traffic. 2. RAM is your temporary desk. ROM is the permanent instruction manual. 3. Use TCP when you need it to be reliable, like email. Use UDP when you need it to be fast, like streaming. And 4. Hardware is the physical body. Software is the mind that tells it what to do.
And that's a wrap. You see how it all connects now, from the physical chips to the software that runs them to the networks that link them all. You have the big picture. You've reviewed the core ideas. Walk into that exam, take a deep breath, and be confident. You know this stuff. Now go ace it. Good luck.